all the experimental data which I will show today, they were obtained when I was a postdoc at the University of Manchester.
From you speak a little bit louder, please.
A bit louder, okay. So I recently moved from Manchester to Lancaster due to a fellowship which I got from the Royal Society. And today I will be mainly talking about drug experiments in our attempt to find Bose-Einstein condensation in this double-layer graphene systems. So this is outline of my presentation. So first I will quickly tell you why we're actually interested in graphene double-layer systems, what makes them so special compared to everything that we have been studying before, which of course you have heard already several times today. Then I will show you some experimental data, and we use two experimental techniques actually to probe this kind of systems. And one of them is Coulomb drug, which you have already heard several times today. Another one is so-called measurements of quantum capacitance. And then I will show you whether or not we actually see any signs of excitons or condensation in our experimental data. So I don't think I really have to tell a lot about it, why people use double-layer structures and what they are looking for. So the subject is rather old. It's definitely more than 20 years. It has been, this double-layer structure has been created in gallium arsenide systems, as you have learned already today, in two types of systems. So either electron-hole bilayers or so-called double quantum wells. These are one of the first experimental data measured on double-layer systems as a drug. You have seen actually this plot already today. And the reason we are interested in this kind of system is obviously interactions between two layers, Coulomb interactions. So if systems are not strongly interacting to each other, then we can study electron-electron scatterings, basically by measuring Coulomb drag, or if they are strongly interacting the systems, then it is known that they support coherent state, which sometimes referred as excitonic condensation. So we are really would like to get to see this in our double-layer graphene devices. We're not quite there yet, obviously. And then tunneling spectroscopy is also very interesting because it actually gives us some details of electron gases that we are studying. So it all started in 2010 when a group from Columbia had exfoliated graphene on a thin slab of boron nitride. This was the first so-called heterostructure. Before that, people always studied graphene on oxidized silicon, and mobility was not so good. It was like 10,000 only. So when Columbia group actually exfoliated graphene on boron nitride, the mobility immediately increased by the factor of 10, and everyone realized that it's actually very nice and interesting. But Manchester group made one step further. So we knew that there are lots of materials actually which can be exfoliated just like graphene in the form of atomic planes. Not only boron nitride, which was used by Columbia group, but some other materials exist as well. So the idea was, why don't we combine actually these materials and to make three-dimensional stuff out of it? So Kostya Novoselo made this cartoon like 3 years ago, just like a joke actually, to tease theorists. But I have to say that now in Manchester we are creating structures which have 10 layers of different materials. So this is not too far from reality. But today I will not talk about all these complicated structures. I will talk about this one. So it's 5 different layers. Basically, these are 2 graphene layers separated by a thin layer of boron nitride, not necessarily monolayer of graphene as boron nitride as shown here. So the thinnest one we used was 3 monolayers. And then the whole structure is encapsulated from both sides with boron nitride just to protect graphene from environment, which makes it of much better quality, much higher mobility. So if you're interested in this kind of so-called van der Waals structures, so heterostructures made of 2-dimensional materials, there is a nice paper from in Nature written by Andrei. So what is so special about graphene boron nitride structure? Why they are so good compared to everything that we have studied before? First of all, it's a separation between 2-dimensional electron gases. So in gallium arsenide structures, the smallest separation that we can obtain is 15 nanometers, because these two-dimensional, obviously we try to make them as close as possible, but we cannot make a barrier too thin because then there will be strong tunneling between two quantum levels. So in order to make two-dimensional electron gases still interacting but not tunneling, the smallest separation in gallium arsenide is 50 nanometers, while in our heterostructures it can be down to 1 nanometer, so factor of 10. And because interaction is related to interlayer distance, obviously we have much stronger interaction in graphene systems. Then the temperature range in which we can study these systems, do any kind of experiments, is much larger. So because boron nitride is a wide band insulator, we can go to room temperature and it still works as insulator. While here the barrier is created due to differences of band gaps in gallium arsenide and aluminum gallium arsenide, which is roughly 0.3 electron volts. So all experiments usually done at rather low temperatures. Then rather technical advantage is that to make contacts to this kind of two-dimensional electron gases, we need split gates, because layers that just grow on top of one on top of another. In graphene, these are just two graphene flakes, and we can make contacts independent to each layer, no problem. And then huge advantage is, of course, that graphene doesn't have a band gap, so we can, by adjusting the gate voltages, we can go all the way from electrons to holes. So we can change the sign of charge carrier just by applying gate voltage or voltage between layers. So this ambipolar can make hole electrons, so which is important to compare, like, do we have actually excitons or not if we just replace electrons with holes. While in gallium arsenide systems, the sign of charge carriers is, as you have heard already today, is defined by the design. So it's either holes or electrons. So it cannot be both at the same time. So these were obviously advantages, but there are some also disadvantages. So we have to pay for all these advantages something. And one of the main disadvantages is that these devices are rather small. So we don't know how to make large devices. The width of our structures like a couple of microns, while gallium arsenide can be grown by MBE, well, centimeters, typically millimeters device. And this actually includes a problem because at low temperatures, due to small size of the device, we have these universal conductance fluctuations, you have seen it already, which basically kills all the reasonable resistances that we can measure. The mobility of our devices is still lower than what gallium arsenide structure shows at low temperatures. All right, so but anyway, this parameter is the most important one, so separation. And with this separation and typical densities which we study, and they are more or less the same in gallium arsenide and graphene systems, we always are in this so-called strongly interacting regime. That simply means that the distance between layers is always smaller than average separation between charge carriers in the same layer. So for different kind of measurements, we use different kind of devices. So for drug measurements, we use this kind of structures. So we have two graphene hole bars. They are separated by a thin layer of boron nitride, which can be, as I said already, down to 3 atomic layers. It's already enough to stop electron tunneling from one layer to another one. The whole structure is encapsulated. The graphene is shaped in the form of hole bars, so we can apply current, measure all the voltages independently, and the quality is very good. So the interfaces between graphene and boron nitride is really perfect. There is no junk trap between. So it's atomically sharp, almost ideal interface between graphene and boron nitride. It can be actually proven. There are lots of structural work done, but I will not stop on it. So the mobility in this kind of devices in bottom layer is between 50 and 100,000. Top layer always has slightly low mobility, so between 30 and 60,000. So for capacitance measurements, the structure are even simpler. So this structure for drug measurements are rather complicated. It takes about 3 months actually to complete the whole structure. It really requires a lot of time. While for capacitance measurements, we just need flakes. We don't need whole bars actually. So we use quartz. Then again, there's 5 layers: boron nitride, graphene, boron nitride, graphene. and then we have a top gate, a metallic top gate on top, which actually just cover overlapping region of two graphene flakes. And we cannot use silicon substrate as in this case. We have to use quartz because silicon substrate makes a lot of, well, there is a parasitic stray capacitance between substrate and on all the leads and contacts, which we should avoid. But the quality of this device, because it actually requires less processing, is really exceptionally good. It's always above 100,000. The only problem is that because we don't have top gate and back gate, so we can't control densities in each layer independently. We have to apply voltage between layers as well, which means that we can't make this layer in between two things. So it should be at least 2 nanometers in order to be able to apply some reasonable voltage between layers and change the density. So another technique which I use for transport measurements in this kind of system is quantum capacitance. Here I will just briefly explain what it is. So this is a normal capacitor. If we have two metallic plates separated by distance d, the capacitance per unit area is given by this simple formula, and voltage is proportional to the density of electrons, density of charge carriers in each layer. You know that. If one of the metallic plates is replaced with material with low density of states, like graphite, for example, then these equations doesn't work anymore. So the voltage which we apply is not all the voltage goes to create an electric field between these plates, but it also sort of spent on increasing the Fermi level because of low density of states, and increasing the Fermi level in this material with low density of states. And this actually has two consequences. One is that this voltage is not proportional to the density anymore of charge carriers in the plate. And second, that this device can be sort of replaced with equivalent scheme where we have normal capacitor with this kind of so-called geometrical capacitance, and then so-called quantum capacitance connected in series, and this quantum capacitance is proportional to the density of states. So by doing this kind of very simple experiment, we know how to measure capacitance. It's very, very easy to do. So by simply measuring capacitance of this kind of device, we can measure more or less straight away the density of states in graphene. And this has been done already quite some time ago. So this is our first work on these quantum capacitors in 2010. So we basically show here that we were able to recover density of states quite easily, properly, because we measure capacitance with accuracy like 4 digits. But also, this is more recent work. This quantum capacitance, which is proportional to the density of states, not always positive. Sometimes it can be negative. It doesn't mean that we have negative density of states. It simply means that electron-electron interaction start to play a role. So when we add electron to a system, energy of a system actually, instead of increasing, actually decreases. So this measurements can be also used to study many-body physics. So to summarize this kind of slide, capacitance is a very simple and reliable technique for studying details of a band structure. And we do it. So another technique is Coulomb drag. You have heard about it already. I will not talk about it too much. So if we have a current flowing in one layer, where the electrons moving in this layer obviously fill the electric field of the charge carriers in another layer, and they get scattered. So when scattering takes place, these charge carrier, I just show them like positive, just because it's easier to understand, but it can be also electrons, of course. So these charge carriers get scattered, so it acquires the momentum in this direction, same direction where this charges moves. And if we would have these two leads, two ends connected with a wire, then we will have a current flowing in this layer in that direction. But because we normally do not connect them with the wire, we just connect a voltmeter, so the electric field actually builds up in this layer to stop these electrons from moving, and this electric field can be measured to the drag voltage. So this has been predicted a long time ago. We can study the so-called drag resistance, and this is a very convenient way of measuring electron-electron scattering rate. So two techniques. This is how our experimental setup works. So we have this bilayer separated by some small distance. And then we have two gates, top gates and bottom gates, and we measure drag resistance, which is a ratio of drag voltage, so voltage measured in the so-called passive layer, and the ratio of this drag voltage to the drive current here. is this drag resistance. So because the separation is so small, we normally do not apply voltage between these two layers. We use top and bottom gate to adjust densities in both layers. So no tunneling between layers. So this how experimental data look like. So blue means negative drag resistance, red is positive drag resistance. So this is drag resistance as a function of top and back gate voltages. I just want you to look at these numbers, so they're quite large. If you remember what has been shown today early in the morning, so normally the drag resistance is of the order of 1 ohm or even milliohms. So here it's 60 ohms, 2 orders larger, I would say at least. But these are voltages, so I told you that voltage is not proportional to the density anymore. So if we recalculate this voltage to the density, this experimental data will look like this. And from here, actually, what we see, we actually notice immediately that at least we have a proper sign of a drag resistance, which means that when we have electrons in one layer and hole in another layer, drag is positive, as it should be from very simple consideration, which I showed you on one of the previous slides. And when we have charge carriers of the same sign, the drag resistance is negative. So now interlayer excitons. So what I have shown you before is just one map of drag resistance at one temperature in zero magnetic field. So we look for excitons, interlayer excitons. When we have electron in one layer, hole in another one, and probably they form at certain conditions some bound state. And the question is how to look for this kind of quasi-particles. So I try actually to show you more or less up to scale. So thickness of boron I tried 1 nanometer. For typical densities, the average distance between charge carriers 10 nanometers. So formation of excitons, just if I look at this, kind of looks plausible. And then there have been already published quite a few works on excitonic condensation in this kind of systems. You have already heard about these works today, and already have some ideas. You know that the predicted temperatures for Bose-Einstein condensation can be just different by predicted by different works, differs by 6 order of magnitudes. So probably experimentally, some of the people who can properly answer the question, do we actually see this condensation at a certain point or not? And what we are looking for. So we are measuring drag resistance, but if we actually do have excitons, as you have seen in the presentation of Marco Polini today, the temperature dependence of the excitons, so temperature dependence of the drag resistance should actually diverge. So we have this quadratic dependence here, but then with decreasing temperature, drag resistance should actually increase rather than decrease. So if this doesn't work, so this is a situation for B equals 0, then we have to apply magnetic field. So magnetic field, usually what it does, it actually sort of try to localize electrons. So it actually quenches the kinetic energy while interaction is still the same. So it actually helps to form exciton. But also there is another trick which has been used by Jim Eisenstein in the 90s. So he had this gallium arsenide system, double quantum wells, and what he actually did, he applied a magnetic field. So he didn't have any holes. It was both layers with electrons. So he applied magnetic field in such way that in both layers, the lowest Landau level is half filled. So there is an equal number of electrons and holes, and then electron in one layer find a hole in another one. This way they form excitons, and at low enough temperature they actually form condensate. And he actually showed it quite nicely in a number of papers that this is indeed the fact. But what is interesting about graphene is graphene has half-filled lowest Landau level at the neutrality point, so at the Dirac point, which means we don't have to really look for this magnetic field or specific density to find it. It's already there in the neutrality point. So this is the strategy, what we have to do. First, we have to check if we have already some signatures of excitons or condensation at room temperature. Then we have to stay close to the Dirac point, because when we increase the density and these charges go closer to each other, the interlayer interaction becomes stronger and there is a stronger screening. So a certain point we just lose the interaction. Then if at room temperature it doesn't work, we have to go to as low temperature as possible, and even if at low temperature it doesn't work, we have to turn on magnetic field and see what happens. So this is a strategy, how to do. Otherwise it will take ages to study the whole thing. So first of all, room temperature measurements. These are the drag data. So we have to compare basically the drag along this line and along this line. And you can see they're more or less the same. So excitons should live here. And we don't see much of a difference between these two, which means probably there are no excitons at room temperature. So then if we decrease the temperature, we again see nice quadratic temperature dependence at finite densities down to the lowest temperature which we can probe this kind of drag resistance, which was roughly 40 Kelvin. So we can't go any further, unfortunately, because, as I said, devices are small and universal conductance fluctuations become significant at a certain point, and it's just a forest of oscillations. We don't see much. And also, if we compare the sort of full scale of drag resistance, not a certain density, but just how it looks at different temperatures, there is some behavior, interesting behavior around neutrality point, but we know that it's actually related to the disorder in the system. And at lowest temperature, you can see just fluctuations, nothing else. So with this, I probably can conclude that we cannot see anything at zero magnetic field. So what happens if we turn on magnetic field? This is how drag looks at quantized magnetic fields. So what is interesting here, so we actually can see it nicely, quantum Hall effect. So where we see all the spots, it's where both layers have Fermi level somewhere inside of Landau levels. So if one of the layers have Fermi level between Landau level, we just see zero. And that's what I have mentioned to Marco Pollini, actually, to test his idea of drag resistance in this regime. So if there is still finite drag when we are in quantized regime, but there is still this upturn, then probably something wrong with the experiment. But one thing which you probably can see is that at this 8 Tesla and 30 Kelvin, we have at this double neutrality point where both layers are at zero density, we have positive drag resistance, while at 3 Tesla and the same temperature, we have negative drag resistance. So double neutrality point is the region where actually we should focus, as I said, according to the strategy which I outlined in one of the previous slides. So the idea is then to measure so-called phase diagrams. So keep both layers at the charge neutrality point and measure drag as a function of magnetic field and temperature. And that's how it looks like. So we spent quite some time to understand this behavior, and now we understand it. So this is a recent work published with theorists from Germany and Netherlands. It's kind of complicated. I didn't have time to discuss it any further today. Then this region, I think we understand well, not really understand, but we have this region where there is a large positive drag. So this is approximately 3 kilo ohms, which is a lot. If you think about two layers which are not even connected to each other, they just coupled with the Coulomb interaction, there is no current flowing from one to another, but that is 3 kilo ohms, not just milliohms, which I have told you about in gallium arsenide systems. So we think that this could be due to virtual excitons. So basically what we have so both layers are at the charge neutrality point, so we have equal amount of electrons and holes in both layers. They probably form excitons, and then they act like two layers. So the drag is just like in two layers with opposite charges. And in this case, the drag should be positive. So that's why probably we see this large red region here. But then what's going here, we have absolutely no idea. So there is some kind of increase and large negative drag resistance at low magnetic field and low temperatures, which is sort of nice because when we so when I just go back here, so in magnetic field we have a new parameter which is magnetic length, and this magnetic length, the ratio of separation between layer to this magnetic length shouldn't be too high, which means that field shouldn't be too high. So if you have a condensation, it should be at relatively low fields. And it looks like we actually have something which only happen at low magnetic fields here. Okay, then another kind of measurements are these capacitance measurements, which I mentioned. I will not go into any details in it, but it just show you some well, rather early devices, let's say preliminary measurements. So this is capacitance measured between two graphene layers as a function of voltage applied between layers and the gate voltage. So these blue lines here, they track position of Dirac points. And then if we apply magnetic field, we see this nice diamond structure, which basically due to Landau quantization. So everywhere we see the diamond means that we have in both layers Landau levels and the Fermi level. And where capacitance is low, it means that we at least in one layer the Fermi level between Landau levels. So the good thing about it is that with this technique we can go to rather low temperatures. It's not 40 Kelvin anymore, we can go to pretty low temperatures, below definitely helium temperatures. So this is more recent device with mobility above 100,000, again zero magnetic field and low temperatures, nice data with two crossing lines as it should be, and then in relatively low magnetic field like already 4 Tesla, we have this central diamond. Instead of one central diamond, we have this 16 dots, which means that the lowest Landau level already at this field is completely degenerate. So we have lifted the spin and value degeneracy. So that's actually bringing me to my conclusion, which I decided to put a little bit like in a graphic mode. So we have this temperature and magnetic field phase diagram. So we more or less understand what's going on in this region. This is not necessarily linear scale, can be logarithmic. So we suppose that excitons live somewhere here, the condensate probably lives somewhere here, and what we do actually with drought measurements, we're trying to approach this region, which is not so easy because of universal conductance fluctuations and some issue with context. So we employ our capacitance measurements to attack this region from both sides. We just started it, so we're not there yet, and there is still things to do. In reserve we have, obviously, as you have heard today, this double layer of bilayers, maybe tri-layers and so on. We can also actually improve our contacts to make inside contacts. We can make probably larger devices as our technique will improve. And we can also probably go to lower temperature. Lancaster is a home of the lowest, the cryostat with the lowest temperature on Earth. We can actually cool down two-dimensional electron gas down to 1 millikelvin. Okay, so that's it. Many thanks to people who contribute to this work, especially to this gentleman who actually spent many, many months for making these heterostructures. And thank you for your attention.
Okay, thanks for that very efficient talk. Is there any discussion? Alex?
So you've got quantum capacitance measurements on the higher quality samples to lower temperatures.
Yeah.
Should you see a signature of the excitonic formation, this discontinuity in the quantum capacitance as you lower the temperature?
As discontinuity, not so much. So what I see actually in quantum capacitance...
At B equals 0?
At B equals 0, I don't see anything.
Even down to 4 Kelvin?
Down to 4 Kelvin, I don't see anything. I have to say that our quantum capacitance devices are not 1 nanometer separation. I said we don't have gates on both sides, so at least 2 nanometers. This is the thinnest what we can do, which probably means that the temperature should be lower. But so far, the single particle picture describes the data we see in capacitance perfectly.
Maybe I asked you the question I asked you in Gothenburg. So, one point of view of what goes on in gallium arsenide is that you have 2 half-fill Landau levels. Another point is that you have a case where you can get an integer filling factor by combining the 2 layers, but not from the 2 layers separately. So that kind of argument suggests the most promising thing would be to have odd total filling factors. I guess some of the data that we were looking at there was odd total filling factors. And is that right?
Which data for so?
The color plot.
This one.
No, the previous.
This
yeah. So are there odd total filling factors there?
No.
That line is most of the data you took is around total filling factor 0.
So this is lowest Landau level. So this is the total filling factor 0 in both
Yeah.
layers. So when you see this one and this one, it means that next Landau level is half filled.
Meaning capital N equal 1 or?
Meaning that so this will correspond to the so completely filled lowest Landau level and half filled next one. That's this point. But I have to say that at these temperatures and in this magnetic field, and for devices with low mobility, we cannot actually get any spin resolved or valley resolved data.
Okay.
So these are all
Okay.
Landau levels 4 times the general.
I understand. Okay. So that's what I was confused about. So why don't you get spin resolved? What's different about these samples compared to? It's just the temperature you're at.
So yes, we basically can go to much lower temperatures than we have now.
Understand.
But I have to say, if I try to go to lower temperature and look around this point, just both layers are poorly conducting.
Okay.
Maybe it means something, but we should still have.
Okay. One final question.
Yes, I just maybe missed the point. What if there is a condensate, what do you expect to see in the capacitance measurements?
So one of the things we expect to see is tunneling, because when we actually measure capacitance, we also measure so-called losses. So with really strong tunneling current, we will see losses. And then if there is a condensation, that probably should be some kind of changes or jumps in density of states, which we will be not able to explain in a single atomic picture, so a single particle picture. So that's all these deviations, that's what we are looking for.
Okay. So thanks again for a very nice talk. Next talk will be given by Arkady Shenenko.